lecture today. Of course, we are starting our last topic of this semester that I call logistical regression models. Okay, so, I told you the other time, statistics is more or less like a story that goes on and on and on. In today's topic, or let me just say in this topic in general, I'm actually going to walk you through some basic concepts. We're going to look at models. We're going to look at how do we conduct statistical inference or using logistical regression models. I'm going to walk you through illustrative examples. And I'm also going to walk you through what I call types of logistic regression models, where we're going to talk about the ordinal logistic regression and the multinomial logistic regression. So what I'm presenting to you now is what we actually going to go over the next few days. Like I said, this is the last topic in the semester. Okay, so let's get started with what we call the binary logistical regression. You know, before we consider choosing a model, it means there exists a problem. Okay, we actually want to provide a practical solution to practical problems. And that is the reason, if I want to do that within a statistical framework, then we're going to use model. Okay, but let me tell you this. The kind of models we use in statistics actually depends on assumptions underlying the use of that particular model, particularly when I'm interested in figuring out relationship between variables with an attempt to make a prediction. Then we need to put into consideration the nature of the response variable. If you take a look at what we've been doing before now, when the nature of response variable is continuous, I'm going to say that again. When the response variable that we also call dependent variable is continuous, of course, we can make an attempt to fit linear regression. I'm going to say that again. Fitting linear regression, or not only linear regression, even analysis of variance, fitting any of that requires that the nature of the response variable should be continuous. It shouldn't be categorical. But what if in a situation where it is categorical, then we actually need to look beyond linear regression. But today, I'm also going to demonstrate to you why using linear regression for categorical response variable could be problematic. I'm also going to walk you through that today. And how do we arrive at the appropriate model that we're going to use for such, that we call logistic regression? I'm also going to walk you through that. But let me first walk you through an example of what the response variable can be. You know, I'm focusing on binary logistic, The idea behind the binary actually means 2, which means the nature of the response variable is 2. You know, when you talk about response variable here, we're talking about outcome. Outcome has 2 possible nature. An example is what I'm presenting now. Yes or no. Oh, do you watch a basketball game last night? Oh, no, yes, no, yes. I'm expecting the response. Maybe I didn't go to, maybe there was a basketball game last night, and maybe I didn't watch the game. And I'm trying to ask some people that watch, whether they watch the game or not. I'm actually expecting their response to be categorical. Okay. Another example, the presence of a cancer and the absence of a cancer. It's either a patient has somebody have cancer or not, or somebody have a disease or not. That's categorical with 2 possible outcomes. What about success or failure? Somebody can write an exam and fail, or write an exam and pass. You cannot write exam, pass and fail at the same time for the same course. That's not possible. Now, it's either one is dead or one is alive. Okay? I'm happy that all of us were alive. Okay, so dead or alive, pass or fail. When you apply for admission into graduate school, it's either you are offered admission or not. But I know before they can offer you admission or not, they will have to consider some explanatory variables. So these are more or less examples of what the nature of the outcome that I call the response variable can be. I will advise that you also cite your own example. I'm going to give another example now. You apply for student loan. It is not all students that apply for student loan that are granted. Okay, so or you apply for bank loan, or you apply for mortgage loan. So what I'm just trying to say, situation where the event has 2 possible outcome. Okay, if I want to look at the relationship between that particular dependent variable that is categorical, okay, in relation to other factors, of what I'm actually talking about, fitting binary logistical regression. Now I ask a question here. How does the model change? How do we analyze the data? Okay, which we're actually I'm going to answer here. So we have a lot of examples that can be cited. I'm actually going to walk us through an example where the response variable is talking about the satellites, having satellite or not. Okay, so Alan Agresti 2013 reported data on 173 female crabs collected on an island in the Gulf of Mexico. It described the data set as follows. You can see that. Okay, now the explanatory variables are the female crab color, the span condition, and the carapace weight. Okay, now if I want to run this scenario, okay, for instance, I'm no longer going to be using linear model anymore. But before, there's something I quickly want to point us into. Instead of us, if we decide to go by fitting linear regression, what happened? I'm going to tell you now. Oh, if I decide to run over a traffic light that is red, what happened? Okay, that's just we know what is going to happen. That is why we don't want to violate the traffic rule. But I'm first going to show you what's going to happen. Because the initial model that they fitted was a linear regression model. They call that linear probability model. Why is it called linear probability model? They call it linear probability model because the response variable is more or less probabilistic in nature. They are actually using ordinary least squared. Okay, now when they use ordinary least squared, I want us to take a look at this. Let's say, for instance, we only want to focus on simple logistic, simple binary logistic. What do I mean by that? Maybe I only want to focus on one explanatory variable. Okay. Now, because of the fact that the nature of the response is categorical, we got two levels. We're going to label them 0, 1, 0, 1. Okay. Now, if we label them 0, 1, if you are fitting a straight line for that, if you take a look at that line now, the first violation here, the line can go over 0, 1. It's going to go beyond that. It can, the line is going to go beyond. It can be less than 0. It could be greater than, the prediction that you want to make here. That doesn't make sense because we know the nature of the range of probability should go from 0 to 1. But when you fit a straight line, that very restriction can never be fulfilled. But let me tell you this was actually argued. It is not only that the straight line is going to go beyond 0 and 1. There's also going to be a violation. Okay, that was what I was trying to say here. What is wrong? Like if I fit, if I fit linear regression, instead of going for binary logistic regression, there are a lot of things that will be wrong. Even those others can be fixed. But there's one particular one that can never be fixed. I'm going to tell you those one that can be fixed. Number one, there's going to be a violation of normality of the residual. But that can be fixed. You know how that can be fixed? Going by statistical theory, when sample size increases, okay, when sample size increases, we actually expect the OLS estimator to be approximately normally distributed when sample size increases. So which means the violations of normality can actually be fixed when you take a very large sample. Another violation is there's going to be a violation of constant variance. And even before I go into the violation of constant variance, how do I know there will be violations of normality? Because the probability distribution of the residual and the probability distribution of the response variable, they must be the same. I'm going to say that again. The probability distribution of the response variable and the probability distribution of the residual have to be the same. And this is the reason why there's going to be a violation of normality, because the response variable that I'm talking about is not a normal probability distribution, which I'm going to demonstrate to you now. Okay, in statistical analysis, if there's two possible outcomes, okay, that's going to be Bernoulli distribution. X follows Bernoulli distribution with parameter P, where the f of x is basically going to be p raised to power x, 1 minus p raised to power 1, and that s star from 0 to 1. This is a distribution now, or let me be using y because I'm talking about the response variable y. So this is the distribution of the response variable. This is not normal. This is Bernoulli. We use Bernoulli distribution to model, variable with two possible outcomes. Two possible outcomes, either this or that. Now, the mean here, the expected value in Bernoulli is P. The variance of Y in Bernoulli is P into 1 minus P. Well, let me tell you this. When we fit a linear probability model to a situation where the response variable is categorical, you can never have a constant variance. Every individual or every observational unit will have their own variance. In that situation, instead of having this, I'm actually going to have the variance of y given x will be equal to pi 1 minus pi, where I go from 1, 2 to n. Individual, every unit, we have their variance. In a situation where every individual have their variance, then the constant variance assumptions has been violated. But there's a good news. The good news is that can also be fixed. Do you know I said normality can be fixed when you take a very large sample size? Heteroscedasticity can also be fixed using what I call the weighted least squared. If I feed weighted least squared, there's a difference between a weighted least squared and the ordinary least squared. Okay, there's a difference between the two. The weighted least squared and the ordinary least squared. This is what happened. I'm going to show you something now. Okay, this is yi equal beta naught plus beta 1x. Those of you online, can you confirm if you're actually seeing what I'm writing on the board? Those of you online, can somebody confirm? Can you see what I'm writing on the board? I need somebody to confirm now among those who are online. Okay, let me see a shout came in. Somebody say I can't. I have to see. Okay, now I'm gonna rewrite that. Those of you online, what about now? Can you see what I'm writing now? Can you see what I'm writing now? Oh, I can see. Yes. Okay, now plus beta 1x plus the error. Now, this is like fixing a linear regression model, right? Where y is categorical. I said the error here will not behave well. Fitting linear regression to that, we call that linear probability. We call that linear probability model. We call that linear probability model. Now, I said the error will not behave well. Why? Because there's going to be violation of normality. I said that can be fixed. Okay, that can be fixed when you take the last sample size. But what about violation of homoscedasticity? Okay, now, but I also said, why is it that there's going to be a violations of homoscedasticity? Because the variance of yi given x now will be pi 1 minus pi, okay, where every individual or every observational unit that you use, we have their own variance. And I also said this guy can also be fixed. How can I fix this guy? If I want to fix this guy, this is what I'm going to do. I will run linear regression. I will get a y cap. Somebody know what I mean by y cap? Predicted value. Okay, I'll get a predicted value. Okay, when I get a predicted value y cap, the predicted value y cap is the same thing as this guy, expected value of y given x. Okay, which is also the same thing as p in Bernoulli, which is going to be a p cap in a way. Okay, now when I get this y cap now, okay, if I want to fix the problem, I'm going to introduce a weight. And that very weight that I'm actually going to introduce, okay, the way that I'm actually going to introduce is going to be called WI equal P equal Y cap 1 minus Y cap, which is P cap 1 minus P cap. Okay, if I introduce this as a weight, what I'm going to do, I will go back to transform the linear module. What was the linear module initially? Those of you online, I'm still going to write yours. Okay, let me write for those in class. I will still write yours. Okay, so I got Y equal beta naught plus beta 1x plus the error initially. Okay, this is having problem. So what I'm going to do is I'm going to divide by WI, divide each of that WI, divide each of that WI, divide each of that by WI. Okay, what is my WI? Y cap WI is this multiplied by that. Don't forget, for each individual, you get it predicted. When you fit a linear regression, right? When you get a beta naught, your beta 1, you can get it predicted, right? If you have 20 individuals, you're going to have 20 values for the predicted, right? When you get 20 values for the predicted, you can determine weight for a particular individual. Now, what I'm trying to tell you now, the square root of the weight of that particular individual is what you're going to use to divide divide all this. Now, when you divide all this, like for instance, here you're going to have a new variable that I'm actually going to call Y star. And here you're going to have a new that, and here you're going to have a new S star. And of course, the error that you're going to have now, will behave well. In terms of, you've already fixed the problem of heteroscedasticity. But let me tell you this. Whether you fix the problem of normality or you fix the problem of heteroscedasticity, there is a particular problem that cannot be fixed. What is that particular problem? You can never guarantee, you cannot guarantee this to be in the interval 0, 1. You can never guarantee that. Okay? Whether you fix the problem of normality, you fix the problem of heteroscedasticity, the facts still remain. You can never guarantee that the range of your probability value, the response will be between 0 and 1. And that is the reason why fitting linear regression is problematic. It's more or less synonymous to, for instance, I was not born in the United States, and some people say, oh, we want Professor Kazim to be president of the United States. And some people were now justifying, oh, because Professor Kazim is handsome, is very quiet, is that the facts remain, whether I'm quiet, whether I'm handsome, whether I'm whatever, the fact remain that that is against the Constitution of the United States. I cannot be the president. If people are trying to beautify me, they are just beautifying nonsense. So the fact, if you take a look at the model, what I'm trying to say is statistical analysis, when the functional form is wrong, the functional form that you fit for a relationship is wrong. Even when you make a lot of attempts to beautify that, the first to remain is wrong. And that was why I said the other time, before you can begin to investigate whether assumptions hold or not, 4 or false arrive at your final model. Is that not what we did? Like if you repeat a measure, before you begin to investigate whether assumption hold, okay, make sure you 4 or false among the candidates model, get the best model. Let me tell you this. I used to give this example and I love that example a lot. Somebody commit an offense in the state of Minnesota. Even though the person was tried in California, It was tried in New York. It was tried in Alabama. Let's say the best out of Minnesota, maybe it's coming from California. Does the best of the wrong translate to right? Does the best of the wrong? The fact remains that person broke Minnesota law. The person did not break the law of other states. Even though if the person run to other states, Minnesota will actually seek for his or her extradition to Minnesota. If you get the best in other states, the facts remain that the other state does not have the territorial jurisdiction. And the same thing is what we're talking about here. Now, what do we now do? What we're going to do is we're actually going to use a brand new model that we call logistic regression. And in that very brand new model, we're no longer in the realm of linear anymore. We are now in a generalized linear model because we're going to generalize linear model. We're going to transform linear model. Okay. We're going to transform its structure. You know, I'm going to give you another example. This is how I understand my statistics. Let's say this guy does sports, and this guy now has a cut, a cut, and blood is coming out. And when the blood is coming out, it could lead to other diseases, right? Maybe like headache, whatever. And you know what doctor is doing? The doctor is just treating the headache. He's treating other disease, but neglecting the cut. When he succeeded in treating the headache and he did not even treat the cut, the problem is still there. Does that make sense? So that's what we mean. Okay, now we are like the nature of the response, like I said, is going to be either 0 or 1. We're going to label that. That's exactly what I'm trying to show you now. Okay, and if that is what I'm trying to show you now, if you take a look at the board, the probability achieving success, I was using P the other time. You can say pi, a function of X, because that probability depends on X. Oh, what is the probability that when I apply for student loan, I will be given? That is a function of so many other variables that I call X. Okay, and which means I can say the probability of Z equal to 1, given they've already observed, maybe I apply for mortgage loan. Okay, if Z equal to 1 means I will be giving. If Z equal to 0, I will not. Now, given X, what is X? Maybe X is my credit history. At times, the independent variable could be more than 1. Okay. Now, like I said, this is going to follow a Bernoulli distribution. That's what you're seeing here. The probability of Z equal to Z will be pi raised to power X, 1 minus pi raised to power 1 minus X. That's a Bernoulli. And that's why we say the distribution cannot be normal. Okay. Now, in a way to transform the linear architecture for us to be able to address, the restriction that we talked about the other time. What was the restriction? 0 and 1. We want the range to be between 0 and 1. Like I told you, when you fix normality, when you fix a constant variance violation, that does not guarantee that you're going to have the range in the 0, 1. And the only way we can have the range in the 0, 1 is to consider odd. What do I mean by odd? Oh my God, odd is going to be the ratio of the probability of success divided by the probability of failure. And that was why you see pi of X divided by 1 minus pi of X. If the pi of X is the probability of success, 1 minus pi of X will be the probability of failure. And when I do that, the range of odd is going to be in the 0 to infinity. Okay. Now, I now need to take the log of that very odd. Okay. The log of the odd now, okay, will now be in the range of negative infinity to infinity, which means initially the model was non-linear, if I now use the log of odd, it has now been linearized. I'm going to tell you again, take a look at that. Initially, we're not supposed to fit a linear. It should be non-linear. Non-linear because the nature of the response is categorical. Then I decided to take the odd. I take the log of the odd. When I take the log of the odd, we have a linear relationship with the module. But initially, the relationship between the response, okay, and the module was non-linear. But it became linear after taking the log of the odd. The log of the odd is what we call the logit. Okay, we call that logit. Now, I'm presenting to you now a brand new module, which is this guy here. The logit, which is going to be the log of the odd ratio equal beta naught plus beta 1x. In fact, one of the assumptions that we test in logistic regression is there must be linear relationship between the log odd and x. Does that make sense? I'm going to say that again. Initially, when I've not transformed, okay, the relationship was non-linear. But after transforming now, using the log of odd, the log of odd is linearly related to x. That is one of the assumptions that we're actually going to test. Now, when I solve for pi x, now, when I go mathematical, solve for pi x, I'm actually going to have the inverse of the logit. You know what? Which is this guy, the inverse of the logit that we call pi of x equal to that. That is what we call the probability model, the probability form of a logistic regression model. There's a difference between the first one and the second one. You know, when you take a look at the first one, the logit, pi of x equal to the log of that, that's a log odd model. That's a logit model. But the one where you see the inverse of the logit is a probability model. Let me give you an example. Let's say I apply for mortgage, and if x represents my credit score, okay, if x is my credit score, what would be the pi of x? The pi of x would be the probability that I will be granted the mortgage loan given they have observed my credit score. Any question? Any question? If the probability is very close to 1, then I'm more likely to be given the loan. If the probability is very close to 0, then I'm unlikely to be given the loan. So in logistic regression model, I wanted to wash out. We can use 2 different models. There are 2 forms of the model. The logit one that we call the log odd, and the probability form that we actually call the inverse of the logit. Now, the next thing I'm going to tell you now is how do we now obtain for instance, if I want to talk about the percentage change in odd, okay, how do I find the percentage change in odd? The moment I know my beta 1 in the model, I'm just going to exponentiate my beta minus 1, take the absolute value of that. What does that mean? It actually means a unit increase in x, okay, increases the log odd, okay, that the response is a success by beta 1. What does that mean? Oh, increase in my credit score, okay, a unit increase in my credit score. Maybe my credit score go up by 1 unit. I think, you know, credit score, the one that go from 300 to 800, okay, where they're going to have poor, fair, excellent. Okay, if there's an increase in my credit score, how does that affect? Okay, how does that affect the log odd? Okay, then I'm going to look at the values of the beta 1. So what I'm trying to say, you know, a unit increase in x increases the log odd that the response is a success by beta 1. Then multiply the odd that the response is a success by the exponentiation of beta 1. So if I want to find the percentage change now, or what I'm just going to do, okay, the percentage change in odd is going to be the absolute value of the exponential raised to power beta 1 minus 1. Now, I just saw, if you take a look at what I'm presenting here, this is simple binary logistic model where I only have one explanatory variable. Okay, what if in a situation where I got more? Because I know when I apply, like for instance, when you apply to graduate school, they're gonna look at a lot of factors before you can be considered. They look at the prestige of your undergraduate institution. They look at your GPA. They look at some other thing, information. Now, because of that, I'm gonna have this guy. Oh my God, take a look at what I'm presenting now. This is more or less looking like what we normally have in a multiple linear regression, where we got a lot of independent variables, but except that this is a multiple logistic regression. What make it a multiple logistic regression? Because you got more than one explanatory variable, but the nature of your response is still categorical, 2 levels. Any question on this? Okay, now I want to show you the data architecture now, subject 1 to subject n. The subject 1 to subject n may be students, undergraduate students that apply to graduate school for admission. Okay, there are 2 possible outcomes: success or failure, right? Success or failure, right? Success or failure depending on some explanatory variables that the graduate school is going to consider. I know some students approach me for recommendation letter. I know they make use of that recommendation letter too. They make use of your GPA. They make use of the prestige of your undergraduate institution and some other. Okay, take a look at that. Okay, now that's what I'm trying to show now. Of course, when success exists, if you can count the number of success, we can also count the numbers of failures, because we find ourselves in a world of variation where we're going to have success, we're going to have failures. Does that make sense? It's just like I have maybe 1,000 students apply to graduate school. It is not all of them that will be given admission. We can actually count the number that are not, and we can also count the number that are given. That's what the data structure is talking about. Now, like I said, this is a multiple logistic regression. You know, the pi into x1, xi1 up to xip is trying to tell you the inverse of the logit, that I also call the probability of being granted admission, okay, giving some explanatory variables, so many explanatory variables. Now, the question now is, if I have either binary logistic or multiple logistic, what method, because if I want to use this, I need to first figure out, I need to estimate my parameters in my model. What are the parameters? The beta naught, the beta 1, and so on like that need to be estimated. Oh my God, we can no longer use ordinary least square approach, because the ordinary least square approach cannot guarantee the 0-1 interval for the response, even though we're able to fix assumption, violation, for normality, for constant variance, but all those ones are fixed, but that does not fulfill that the response variable is going to be in the interval 0-1. And what are we going to use? We're going to use a maximum likelihood method. Okay, the maximum likelihood method is basically going to be used in estimating parameters in the logistic regression model, not the ordinary least square. Not the ordinary least square. Not the ordinary least square, because of the fact that the ordinary least square cannot guarantee 0-1 interval range for the response. That is the only reason. If you want to talk about normality, if you want to talk about constant variance violation, I told you that can be fixed with the OLS. Now, what I'm demonstrating to you now is how does the likelihood function work. Of course, I'm actually going to write the joint probability function for the underlying probability distribution. The underlying probability distribution for the response is binary. when you take a look at this now, that's a Bernoulli. This is like a writing Bernoulli in a joint form. Okay, then when we have it in a joint form, then we're going to take the log of the likelihood. Taking the log of the likelihood, that will lead to addition because, the product, when you log, the log of A multiplied by B multiplied by C is going to be the log of A plus the log of B plus the log of C. That's what you have. So in the end, you're actually going to have a result. But let me quickly explain. With the logistic regression, you've had about odd, you've had about probability. What is the relationship between the probability and odd? Okay, for instance, if I want to start with the probability of success, then determine the probability of failure. Of course, I know success and failure are mutually exclusive. Success and failure constitute the sample space, right? And they are mutually exclusive. One complement the other. When I had a probability associated with success, so the probability associated with failure, they should give one, right? And because of that, when pi of s is 0.9, which is the probability of success, then the probability of failure is going to be 1 minus that. They're complementing each other. That would be 0.10. And do you know when I have the probability of success, I got the probability of failure? Oh my God, I can set up the odd ratio. Because the odd ratio is going to be the ratio of the probability of success to the probability of failure. Look at what I have in number 2, odd, probability of success, divided by the probability of failure. Okay, that's going to be 0.9 divided by 0.1. That would be 9. Odd ratio here is 9. What is it meaning? It means the odd of success, to failure is going to be 9-1. That is a meaning. Any question? That is a meaning. But you know what? For us to be able to guarantee the fulfillment of 0-1 for the response Y, we're actually going to use the log of odd. We're interested in the log of odd. Does that make sense? Because the log of odd will return the situation back to negative infinity to positive infinity. We'll return that situation back, but the fact that can guarantee us to have 0-1. I'm going to show you the data set now. I'm going to show you different values for probability, the odd, and the log odd. This is going to be super easy. When the probability is 0.01, what would be the probability of failure? That would be 1 minus that, right? What would be the odd? The ratio of the probability of success to the probability of failure. Now, I want you to take a look at this. When the odd is 0.5, when the probability is 0.5, what does that mean? Oh, when the probability of success is 0.5, the probability of failure is also going to be 0.5. What will be the odd ratio? The odd ratio is going to be 1-1. Does that make sense? Because 0.5 divided by 0.5, that will be 1. And when I go 1 now, what is the log of 1? The log of 1 is going to be 0. Take a look at that. Okay? Now, you can now see now, when you have the odd, for instance, the odd was actually for this guy. Okay? The other time, we started with that probability, all right, of 0.9. 1 minus pi was the probability of failure. We got the odd ratio, right? 0.9 divided by 0.1. We got 9, right? What is the log of 9? We're talking about natural log of 9. That would be 2.1972, right? Okay, now if I know the log of odd, now what I'm trying to say in my example, the log of odd is 2.1972. But how do I get my odd back? When I have the log of odd, oh my God, I will exponentiate that. When I exponentiate that, it will take me back to my odd. That was what you're saying in number 2. Now, exponential raised to power 2.1972 will give you your 9, which is your odd. And do you know when I have my odd, I can calculate my probability back using the inverse of the logit. I'm only going to plug in 2.1972 into that. That will give me back my 0.9. Take a look at what we've been doing now. It's like you put a water inside your refrigerator, the water become ice, and you bring the water out. When you bring the ice out, right, the ice is going to turn back to water. Take a look at that. Now, before I go, I want to walk you through a real life example. How do we actually implement logistic regression in R? Now take a look at this. We actually want to look at the effect of weight on whether satellite is present or not. What is the nature of the response? Categorical. Satellite could be present or not. Oh my God. I wanted to look at the code. How is this code here different from the code in the linear regression? Take a look at that module.1. How is it different? We are no longer using LM. We are now using GLM. What do we mean by GLM? That's a generalized linear module. GLM means generalized linear module. Okay, generalize. Okay, generalize linear module. That is what we call GLM. That is what you're going to be using. You see GLM, and when you write GLM, you also have to indicate family equal to binomial. You just have to do that. Look at that here. Family equal to binomial. When you now run that, you do the summary of module.1, it will give you this result. Now, take a look at that result. There is something I want you to take note in that result. The linear regression will come out with T, right? But this is a Z. Can somebody spot the Z on the board in the output? Do you see that Z? Estimate standard error Z value instead of T value. Please take note of that. T value, we have a Z value now. It is not a T, it's a Z. When you actually run a general linear model, you're going to have a Z instead of a T. Take a look at that. And you're actually going to have the AIC, you're going to have some other stuff. Now, when we have this now, I wanted to take note of this. What do we call the estimate? Minus 12, 3.508 is 0.4972. We don't call them estimate. Do you know what we call them? We call them log odd estimate. Log odd estimate. They are not just estimates. What did I say we call them? Log odd estimates. So we call them, okay, we call them log odd estimate. They are log odd estimate. Okay, they are log odd estimate. Minus 12.3508 is 0.4972 are log odd estimates. Okay, now the next thing I want to do now is actually how do we, the log odd estimate are just a point estimate. We can also get what I call, take a look at this now. Okay, these are the coefficients that I just talked about. The other, negative 12. If you take a look at the first one, but they are on the logic scale. That's why I call them log odd estimate. Now, how do I get odd from the log odd? The regression output will give you log odd. If I'm interested in odd, what am I going to do? I will exponentiate. That was why exponentiating that, round it to 3 decimal, that gives me 0.0001.644 is 0.001.644 a odd estimate. Then I can get the interval as confidence interval for that. That is what you see here. Okay. Then how do we interpret that? I think my time is up. I have 2 more slides. I will start from this on Friday, interpretation of that. Any question before I go? Any question on how to get the log odd estimate, the odd estimate, and also to get their corresponding interval? Any question on that? Okay, before I go, I'm going to remind you again, the final practice questions will be released today without solution. There's going to be 3 problems in exam, 3 major problems in exam. One of them will be PCA. Another question will center on repeated measure. Another question will center on logistic regression. Does that make sense? 3 major problems. Make sure you stay safe and have a lovely day. Bye for now, everyone. Give me 1 second.